About to leave, already packing. Come with me, I'm not really asking. We'll get away to a place where we don't know. About to see the world in action, what we can be, life with no distractions. We'll get away, this is what we waited for. Take my hand, we'll make it somehow. We can't miss out. I'm done living life with the lights out. Die with my own doubts. Be free with me. Let's be free with Not looking back, eyes on the freeway, Bonnie and Clyde, a classic cliche. We're on the run, this is what we waited for. Take my hand, we'll make
By a whole grade.
I've improved.
Improved.
By a whole grade.
By a whole grade.
By a whole grade.
My teacher isn't just Mr. Maddock. It's a whole teaching team made up of James, Mike and Marta.
My classroom's all about doing and applying. My days standing at the front of the classroom with a PowerPoint are long gone.
I master every concept by learning at my own pace.
I spend 100% of my class time interacting and supporting individual students.
I move on only when the moment is right for me, not the whole class.
I know what each and every student is mastering and struggling on at every moment.
I know exactly what I need to learn next, and I can go back and review material at any time.
I spend my teaching time supporting and inspiring, not planning, delivering and marking.
I can learn from anywhere at any time.
I can switch off when school closes, knowing they are learning from the best.
My teacher has my homework marked before I get to class.
I set every piece of homework at the start of the year.
I'm 2 weeks ahead of my expected progress.
I can track everyone's progress with a swipe of a finger.
I can track my own progress and set my own targets.
I now have time to focus on developing the skills of every learner in my classroom.
I know exactly what it means to explain, evaluate and analyse, and I'm not afraid of any exam.
My lessons are now far more about the skills and the application, not just the content itself.
I've completely remodeled what it means to be a teacher in my classroom.
Good afternoon, everybody. James here, the EverLearner. Good to see you all. You may notice a bit of a change around me. The shot that you can see kind of here is reasonably tidy. Everywhere around us is a big mess because we're supposed to be on a new office today. We were there this morning. It's really nice there, but the internet doesn't work yet. So for doing this kind of stuff, it's pretty useless. So we're actually at home today, so anything could happen here. The cat is likely to make an appearance. The doorbell may ring. We may get cold called at the door by just about anyone, so who knows who's going to make an appearance today, but it's going to be fun. Usual things apply. Please ensure that you please ensure that you've got your notes pages. The notes pages are available in the description of the video, I think. Yeah.
Oh, yeah.
Yeah, hopefully. Good. And hope so. And they're also available on the usual download spaces. We'll make sure that they're there for you. So you need those notes pages available to you. Secondly, please do subscribe to the YouTube channel. It's really important you do that. It makes a big difference to us to be able to continue to do these things for free. So we really do appreciate that you do that. And thirdly, we would like you to interact with the show. So 2 ways. One is, as always, I'm probably not going to get you to demonstrate this today, Martin's just going to say it. So as always, you can go to the everlearner.com, go to the news button, and under news there is a post there about interactive questions. Go there, fill out some of our exam questions. We receive those, we mark them, we send them back, and we publish those that are really, really nice. So have a look at that and do submit those to us. It would be really, really, really good exam preparation for you guys as well, of course. Finally, during any part of this show, you can tweet, Facebook, or Instagram us at the, and you can do that with the hashtag revision break. We'd like photos, like to see what you guys are doing on your little breaks from revision during the show. We have some little interludes and interruptions during the show, so at those points we'd like you to send us those photos. So we like to see them. You do need the permission of anyone who's in the photo before you send it in. But all that being said, I think we're pretty much ready to go. We've got a lot of content to cover today, so I'm eager to get on with it. I'm already planning that we're going to plan one answer rather than answering it in full, because it is going to be kind of a little bit time heavy, the session today. So I think if we are ready, Marta, and you're ready for us to go, yeah, everything ready to go? Okay, let's move on to the canvas and we'll go from there.
So Newton's laws, and I think it's one of those subjects or topic areas which is kind of taught in a shaky way sometimes. So let's make sure that we simplify this and clarify this and understand this in the way that we need to do. So look, I guess for me, we are going to look today at definitions and what these laws actually are, but more importantly, we're going to look at application. Okay, so for me, this is all about the application of these ideas so that you guys can effectively apply them in literally any direction you need to. One of the things I think we need to draw out first of all is to clearly understand that Newton's laws describe how all motion occurs. Okay, so one type of motion, for example, let me write this in. So we're describing a notion of all motion, a notion of all motion. I might use that. It's a little catchphrase. We're describing all motion. And of course, one subpart of motion is something like stillness. You might think, what? Well, that's not moving. Well, exactly. So we need to be able to explain all movement and non-movement using these three laws. And that ultimately is why it's so pivotally important for us from a sports science or physical education perspective. Because if we're interested in the science of movement, then we have to fundamentally understand the three base principles by which all motion and stillness is characterized. Okay, so that's what we're looking to do today. As you can see from this little illustration here, we need to clearly understand that there are three laws, N1, N2, N3. And I would also strongly encourage you to learn these words related to each one. So N1, Newton's law 1, which we're going to come to in a second, is referred to as the law of inertia. More about that word in a second. N2 is the law of acceleration, and N3 is the law of reaction. I encourage you to ensure that you can reflect and relate these laws using those three words, but because by remembering that law 3 is about reaction, it kind of pretty much gives away what the definition is, which we'll come to in a few moments' time, and then obviously we can begin to look at the application. So these I feel are crucial. I don't know if a mark scheme is going to give you a credit for saying N1 is the law of inertia. It depends on the specific question, I suppose. But by understanding that that's its name and understanding what the concept of inertia is, which we're going to come to right now, then that's going to make it very, very memorable for us. So this little schematic here is a nice one. Now, let's get on to Newton's first law. So we already know this is N1 because it's the law of inertia. Let's get on to our definition here. An object, sometimes we say a body, will continue in a state of constant velocity until compelled to change by an external force. So it feels wordy. It feels like, what does that actually mean? Well, so effectively what this means is that an object, a sporting object for us, a ball, a body, a person who's running or jumping or whatever, an object will continue in its state of motion, until an external force applies. So constant velocity can kind of mean two things, okay? It can mean the notion of sort of constant speed. Let me change colour actually. It could mean something like constant speed. Just literally switching the vector of velocity for the scalar of speed. Or it could mean stillness. And that is where we want to come to this word. Inertia literally means a reluctance to change state. Okay, so let's actually link that off. Let's link that off. We've got here inertia is reluctance to change state. Okay, so What we're saying here is that once an object is moving, or indeed when it's still, the tendency is for that object to continue in that rate of movement or that stillness, which of course is also a rate of movement. So let's see if we can apply that. Let me draw some kind of dodgy golf tee here. So I've got a golf tee, really badly drawn, I think we can all agree, but there's my golf tee there. And on the top of this golf tee, I'm going to have a golf ball. Okay, so pretty poorly drawn, but you get the idea. Here's my golf ball, and somewhere here we're going to have some grass. So I've got my golf ball, which is sitting in this position here. So I think we'd all agree that we would characterize this movement as stillness. Okay, stillness. In other words, it has constant velocity. The sprint on the block remains completely stationary. The golf ball on the tee remains completely stationary until what? Well, it remains completely stationary until it's compelled to change by an external force. Well, in this case, what is the external force going to be? Well, for us, there's going to be some golf club which clatters into it. Here, this is a golf club. This is a golf, the head of a golf club, by the way. This golf club is going to hit it and contact here, okay? And of course, then we're going to overcome that state of inertia, okay? We're going to overcome that state of inertia. So whatever the contact force is obviously, as we're going to look at the moment, proportionate to the action which is going to occur. But that ball is going to remain stationary, it's going to remain constant velocity, it's going to remain still, it's going to remain in a state of inertia until compelled to change by the external force of a club face contacting the ball. Okay, I suppose you could say a big gust of wind or the tee falls over, but the one we're interested in is the golf club contacting the ball. So that shows us how we've got a state of inertia there. Now, this is just sketching because we're going to put this into much more detail when we look at vertical and horizontal forces. We could even say that, look, there is our weight force, and we're drawing a vector there. There's our weight force. And of course, what we have from here is that we have our reaction force. Our reaction force, we could call it T reaction force from the T, which is equal in size but opposite in direction. These are arrows, by the way. These should be a little clearer here, to be perfectly honest with you. So what do we have there? We have a weight force and a reaction force which are exactly equal, okay? And that means that we can describe that as zero net force. Okay, zero net force. Net simply means total. Okay, so net means total or overall. So on this golf ball right now, there is a zero net force because the net force is the two vertical forces cancelling each other out. So as a result of that, we get a state of inertia, a state of stillness. Once this club head contacts this ball, and this ball goes shooting off through this action force, okay, this action force, then of course we're not going to have zero net force anymore. We're going to have net forward force, which is going to cause that to happen. And of course we're going to get acceleration in that case. In other words, we're overcoming inertia. So what does law 1 tell us? It tells us that an object remains in a state of constant velocity or stillness until an external force compels it to change its state, compels it to accelerate or decelerate. So let's have a look at the second law. We have the law of acceleration. Remember, we have that here, the law of acceleration. What does it tell us? An object will accelerate proportional to the force acting and in the direction of that force. So we have two parts. We have part 1, which is here. An object will accelerate proportional to the force acting. And part 2 is it will accelerate in the direction of that force. So in many ways, this should come across to you as very much common sense. And really where we want to go with this is we want to say that force, this is how we could summarize it, equals mass times acceleration, which of course in most contexts we're going to write as F equals, I can't remember what colours I used, MA. Okay, so why is this important to us in terms of our sort of sporting, and so why is this equation important to us? Well, think through sort of sporting actions, think about runners, think about balls, think about jumps, think about hits. We've got a situation here where we're basically saying the force applied is a product of two things multiplied together, the mass times the acceleration. But of course, in sporting contexts, in basic terms, the mass of objects does not change. In other words, the mass is a constant. And if it's a constant that doesn't change, then really what we've got is we've got force equals acceleration. What do we have in this equation here? An object will accelerate proportionate to the force acting. Force equals acceleration. So let's just get to the basic principle here. I'm just going to give you an example of this. Hit it with more force and it will accelerate more. Now, I don't think that's going to shock anybody, right? So if you think about, what should I use as an example? If you think about a table tennis ball, which you strike your first shot with more force and your second shot with less force, which of those examples is the ball going to accelerate more? Well, it's the first one, right? You've applied more force to the ball via the bat, therefore it's going to accelerate to a greater degree. And Newton's second law states that exact principle. Hit it with more force and it will accelerate more. Or we could say apply less force and it will accelerate less. We could say apply more force and it will decelerate faster. Think about catching a ball, for example. We're decelerating the ball. The more force we apply to it, the faster it's going to decelerate, which is why sometimes we cushion the ball to decelerate it slowly, for example. So let me go back to my very, very bad drawing from before. Let's actually go up here. So, of course, if this club face applies a greater force, action force, remember, to this ball, okay, its outgoing velocity is going to be higher. Okay, so its outgoing velocity is going to be higher because more force has been applied to it, and the force applied is proportionate to the acceleration. Okay, so we hit it harder, it travels faster. There's not going to be any great surprises there. Now, the second part of Newton's second law says that the acceleration happens in the direction of that force. So again, if we think about this example here, in which direction is this ball going to accelerate? What does your intuition tell you once we've got our action force here? In which direction is that ball going to accelerate? And you'll probably be able to tell me what's going to accelerate in that direction, and it's eventually going to come down somewhere over here, right? And you'd be exactly right. So in this sense, if we hit the ball at that angle, it's going to follow that path. If we hit the ball at that angle, it's going to follow that path. In other words, the ball is going to, in this case, the ball is going to travel in the direction that the force is acting. Okay, the direction that the force is acting. So this has certain applications that we might want to think about this direction point. Well, first of all, we want to give direction, so we want to obviously apply the force in the direction that we want the ball to go, or the jump to take off, or whatever. But we also want to do something like a follow through. And why would we do that? Now, if we talk about impulse now, we'd know that force times time, if we apply the force for longer, we get a greater impulse, but also we get a greater accuracy. Okay, so we get a greater accuracy of direction by applying something like a follow-through, because the follow-through, of course, acts in the direction of the intended travel. So law of acceleration works in that way. Finally, we have what we call the law of reaction. And I've found in the past that a lot of times students can regurgitate this principle, but they don't necessarily understand this principle. So let's see if we can get both of those things. We're saying for every action, there is an equal and opposite reaction. Don't forget that comma in there, please. It's important because we want to have good grammar. For every action, there is an equal and opposite reaction. Okay, for every action, there is an equal opposite reaction. So what does that mean in effect? Let me draw my T and my ball in again here. Okay, so pretty ropey drawing. Again, there's my T coming down there. Here's my green grass. And you got me singing there. And here's my golf ball. Okay, drawn even worse than the first time. Here's my golf ball. And what we're saying now is that if our club head, which is here, let me just shade that in, if our club head here if it applies this action force on the ball, then the ball is also applying an equal and opposite action force on the club head. And by the way, that should have been slightly longer, so they should be the same length. And this would be what we call the reaction force. Okay, so we've got the reaction force there. Okay, so we've effectively got the club applying the same action force to the ball that the ball applies back on the club. And you might want to ask yourself, well, therefore all forces are equal, therefore why does it accelerate off in that direction? And the reason that that is of course that this club head has more mass. Okay, it's got more, it has more mass to it, and therefore it has a greater inertia. Okay. Oh, sorry. Let me restate that. It has a greater momentum at the contact point. So in this case, of course, the ball is going to accelerate off and end up over here somewhere. The ball is going to end up over there, traveling on that flight path there. It's going to end up like that because the club head has a greater momentum because it has a larger mass than the ball does. You might want to think, you know, when you press your feet down onto the ground, you take off, right? So if you push downwards, okay, what's ultimately going to happen is the ground is going to push back up on you, and you are going to be the one that accelerates upwards rather than the earth accelerating downwards. Well, why? Because the earth has a lot more mass than you or I does. You or I do. So therefore, it's you that accelerates upwards from that collision of your feet with the earth rather than the earth kind of being pushed away. You might also be able to think, if you've ever... you could actually try this. If you've got like wheelie chairs in your classroom, or you know, you've got two people on wheelchairs, if you're approximately the same mass and you sit opposite each other nice and close and you sort of both push each other on the shoulders, you'll notice that both chairs accelerate away from each other. Why? Because both have the same mass. So in this case, for every action there is an equal and opposite reaction. The club face applies a force of 250 newtons on the golf ball. The golf ball applies a reaction force of 250 newtons on the club face, which is equal in size, 250 newtons, but opposite in direction. So if the action force is upwards and forwards, the reaction force is downwards and backwards. In other words, it's equal in size and opposite in direction. In fact, that's a good thing to think about. Equal in size, sometimes we say magnitude, and opposite in direction. So let's actually do some application of this. Let's have a look at a question all the way down here. Let me make that slightly bigger. Hang on a second. Let me make that slightly bigger, a bit like that. So we've got a question here. Select one of the performers below and explain how a knowledge of Newton's laws could help to improve their performance. So we're in the business here of explaining how. So we're going to be using language like by, through, this means. I could use a because in there because I'm explaining how. If you're wondering where this kind of connecting language comes from, go and have a look at our roadmap service. It's completely free. It's on our website, theeverlearner.com. Go and have a look. It's going to make a big difference to you. So let's have a look here. We have got our first part of our answer. Let's put it in. Laura, so I've chosen the gymnast here. Laura could use N1, so I'm looking at the law of inertia, by, now I'm explaining how, achieving a state of inertia when balancing. So I'm going to get my mark for saying a state of inertia. That's going to help her when balancing. And she's going to do this by having zero net force, which causes stillness or constant velocity. So I've taken my key language all the way up here from N1. Okay, I've got my language of, inertia, zero net force in this example, and I'm putting it into my answer. So what does Laura therefore want to do? She wants to achieve zero net force to get a perfect balance in a handstand or a headstand or whatever. Zero net force. Remember, I'm talking about a rhythmic gymnast here, not just this particular image, which causes stillness or constant velocity. Now, we've got a 6-mark question here. We're probably going to get a sub-max of 2 for each of the laws because we have to apply all of Newton's laws and knowledge of Newton's laws, all 3. So Laura could use the law of inertia by achieving a state of inertia when balancing by having zero net force, which causes stillness. I'm explaining how, I'm using my key language, I'm applying it to the performer. Next example. Use N2 by, again I'm using my by language, by applying a greater force to the ground when leaping. So of course if we get a greater force, what's that going to mean for our upwards acceleration? This means a greater height as acceleration is proportionate to force applied. So in other words, we're saying push harder and you accelerate more in your jump. Okay, that's what we're talking about. I could go on and talk about direction. Push directly downwards and Laura would travel directly upwards. Okay, because that is the reaction force is the one causing her to go up. So therefore, we could talk about the directional aspect of that as well. And my last point, which I really struggled to fit in, you'll see in a second. What have I done? Bear with me a second, folks. My last point. So let me just go across. You see here, I really struggled to fit this in. So use Newton's law 3, N3, by applying the right amount of force to the ground at landing. Okay, so the right amount of force to the ground at landing. So the ground applies an equal and opposite force on the gymnast to bring them to a stop. Okay, so what am I saying here? So when she lands from her jump, for example, we're saying she has to apply the right amount of force to the ground so the ground decelerates her appropriately. She also has to do that in the particular direction. Of course, she's going to apply the force downwards, so the ground applies a force upwards on her and prevents her from hitting and colliding with the floor. That is an excellent example of what we would describe as application of these rules, and we've done that with a gymnast. Here now we're going to have a look at how we do this with a goal defence netball, and actually I'm going to leave you to complete the answer. All I'm going to do here is plan it for you, okay? And I'd encourage you to try and get your 6 marks out of actually putting this in. Julie sometimes plays as a goal defence netball. Apply all of Newton's 3 laws to the performance of rebounding, jumping to catch a missed shot in netball. So let's see what we would have. So I'm going to do my N1. Here's my little plan for how I'd apply it to netball. She's going to overcome inertia with a large force. So actually in this example, I'm not saying she's still. I mean, I guess you could say she gets into the ready position and holds stillness. You could do that, I suppose. But I'm saying here, she overcomes inertia with a large force. So I'm using Newton's first law, but I'm actually saying how she'd overcome that first law. And I'd also say that the external force is the ground reaction force. So when she's jumping, of course, so if we think about, let me do some rudimentary drawing of a netball player. Oh my God, this is going to be disastrous. So here's my netball player about to take off. Ball's up here somewhere. Okay, of course, what have we got here? Well, we've got weight force, which is acting downwards. There's my weight force. And I've got ground reaction force acting from both feet. Ground reaction force. So of course, if our ground reaction forces together are greater than our weight force, we're going to get a direction of movement upwards. Okay, so we're showing that here. So the external force is the ground reaction force. So we want to be able to define that term. Next, let's have a look. Newton's second law. The more force she applies, the greater the height. We looked at that with Laura as well. We can define this with force equals ma. Force equals mass times acceleration. Julie's mass is constant, so the more force she applies, the more she'll accelerate. And the force is upwards. So as we said a moment ago, the force direction is upwards, and we already know that that's from the ground reaction force. Now M3, apply more force down to get equal and opposite force up. So the harder she pushes downwards, the more force she's going to get upwards. Okay, so that's equal and opposite force up. And apply force in accurate direction. In other words, we're saying here we must state the direction. So apply the force downwards so that she gets the reaction force, ground reaction force, upwards. And I would really encourage you guys to have a go at actually writing that answer in. Now, look, you guys have to put that into a flowing structured answer. But if you look at my answer up here, Laura uses N1 by, and this happens by. Use N2 by, so just, you don't need to waffle in your biomechanics. Don't reintroduce the question terms. You don't need to write long statements. You don't need to build around your answer. Get your answer on the paper and structure it in the way that I've shown you here. And in terms of the planning, this would be more than enough to get you those 6 marks on that question, okay? Now, I think the only complex aspect of that is this part here. We've said on this bit, it's not that in rebounding you're in a state of inertia. You could be. I mean, you could say that the Julie accelerates upwards at constant velocity. You could certainly say that. But here I'm saying she's overcoming that inertia, that stillness, that constant velocity with a large force, with a large enough force, actually, I might want to say. Okay, so that's just, I'm effectively inverting or kind of turning on its head that law 1 and saying not that she's in a state of inertia, but this is how she got out of a state of inertia, which of course leads us neatly into law 2 also. Okay, that's enough on this part. Straight back.
Okay, so that's that. That's Newton's laws in a nutshell. I didn't put it much in a nutshell. It took far longer than I intended to. Never mind. Yeah, what have we got?
Right, I have a question. I'm wondering. I struggle with all these sort of physics ideas, and I can't quite understand if the mass of the club, if I'm hitting a golf club, if the mass of the club is always the same, I suppose if I hit the ball harder or softer, it will be because the force I'm applying is different.
When you say you're hitting it harder or softer, do you mean you're propelling it less horizontal and more horizontal distance?
Yeah, that's exactly what I meant.
Okay, so there's a couple of variables in there that we haven't looked at there. One is elevation and the loft, how high you hit the ball, because of course the ball can travel both vertically and horizontally, and the combination of those ultimately means diagonally. So it's gonna travel a certain distance in terms of its height and a certain distance horizontally. The way I tend to think about it, to simplify this, is think about the horizontal distance which the ball travels if we're using the same club over and over and over again, without changing like the elevation of the club face and things like that. So if you pick whatever club you're interested in, but pick a driver for argument's sake, what's going to make it travel a greater horizontal distance, assuming that everything else is equal? It would be that there was more force applied by the club head to the ball, and that's going to happen because the club head is traveling at a greater velocity at the time of impact. Now, there's one other variable in there, and those students out there who study impulse will already know about this, and that is it can be related to the amount of time in which the club is in contact with the ball. So that's the concept of impulse, force times time. But the main principle to think is if all other variables are consistent, if you strike something with more force, it will have a greater outgoing velocity. Therefore, it must accelerate more. So therefore, the more force, the greater the acceleration. If we've got greater acceleration, therefore a greater outgoing velocity, it means there has to have been more force which has caused that, or it could be a change in mass, but of course the mass is consistent.
Right.
You don't look convinced.
No, yeah. I'm just thinking. So, if I apply more force, the ball also reacts differently depending on how much force I apply, so even if it's a still object.
Yeah. So the ball will react differently, except that it will also be completely predictable how the ball will react. So if you were to strike the ball at 90 degrees with a force of 100 newtons, the ball will react onto the club face with exact opposite direction and at what did I say, 100 newtons? With exactly 100 newtons by definition. But as we said before, the reason the ball accelerates away is it has less mass than the club, and in this case we'd actually combine the club and the person hitting it. So you'd have that greater momentum that with the club, and therefore the ball is the thing that's going to accelerate away. So yeah, if you've got two things of completely equal mass and they push against one another, they will both accelerate equally away. So we're not on wheelie chairs to demonstrate it, but if you and I kind of pushed each other on wheelie chairs, someone might be able to practice, but if we pushed each other like that, we would both go away because we're approximately the same mass. Approximately.
Okay.
Maybe one of us would accelerate more than the other.
Well, we can try one day.
Yeah, maybe. Any other questions?
No, not really. No.
Yeah, sure?
Yeah.
Okay. All right. I've no idea what. The clock's up there. Actually, I forgot we have a clock in here. Okay, fine. Well, we can move on whenever you're ready. If you're sure.
Yes, I am sure. Yes,
okay.
I was just looking if we had any questions on Twitter, but no.
We're a bit out of our rhythm in here because we're not in the same location. We don't have the same things as we would normally have. Hopefully by Wednesday we will have. So we're slightly out of kilter today. But nevertheless, there we go. So we're going to move on to... Sorry, go on.
No, yes, actually, we do have a question through Twitter. Can you explain the laws in relation to a swimmer?
Mm-hmm. Yeah, so this is important. So
diving off a block.
Okay, so that would... do we have a name of the person who's asked?
No, I haven't got it, no.
So a swimmer diving off the block, I mean, we could take numerous angles here, so I'll take the most obvious one. So this is how I would apply all three laws to that circumstance. So first of all, we would say that the swimmer would remain completely stationary on the block until compelled to change that state by the block pushing on their feet to propel them forward. That, of course, is going to be a reaction force to the feet, the legs pushing downwards on the block. So they're going to remain completely stationary. That's going to be zero net force acting on that body in that stationary position. If you're a swimmer out there, you'll know if you twitch or move, or indeed if you leave the block, you're going to get buzzed for a false start in that situation. Second law, we would say the acceleration of the swimmer from the block is going to be proportionate to how hard they push, or how much force they actually apply to the block, and it's going to take place in the direction that they push. So if they push backwards and downwards on the block, then they're going to be propelled forwards and upwards until they come down into the water. And that's going to be because we've got that reaction force acting on them. So the rate at which they leave the block, the outgoing velocity, which of course is a product of the acceleration, is proportionate to the amount of force that they apply to the block, and it takes place in the direction of the block. Now, someone who's better at swimming than me, I'm terrible at it, would tell me that maybe you don't go up and down like that. You kind of go more forwards, right? I guess that. So if you press backwards on the block, you go forwards from the reaction force. And the third law would be that every action has an equal and opposite reaction. So in other words, we'd say as the swimmer pushes backwards with a certain degree of force, let's say 500 newtons, the block is going to propel them forwards with the extent of 500 newtons exactly, and of course that's going to produce the amount of acceleration that they achieve. Another thing you could say on Newton's first law, so once they're in the air, they're going to continue in a state of constant velocity until an external force acts. That external force is going to be the water as they slip through the water, which is going to, of course, apply a drag force on their body, so that you could even consider that to be that continuous constant motion until their hands, their fingertips, hit the water, and then, of course, that's going to be the external force acting.
Good.
Okay?
Great.
All right, great. So we need to move on because we've got a chunk left. I'm going to try and go faster on the second bit than the first bit. So let's see if we manage it. I'm ready when you are. Okay?
Ready.
Good. Oh, so we had a bit of a sound problem there, did we? Okay, do you know what you're doing?
Yes, I just need a couple of minutes to try and sort out the sound.
Okay, let me do something else. Georgina, are you there? Yeah. Come and give me a hand a second. So sorry about that, folks. We'll get that started again for you in a second. Told you we're in the new environment. Georgina, come here. We're going to do a little demonstration. Hold the ball like that. Okay, let me get this sort of out of the way. You need to come forward so you're in the picture. Okay, so hold the ball like that. So in this moment here, we have a situation where that ball is at 0 net force. So this is an excellent. Well, you could apply all three laws to this moment, to be perfectly honest. So that ball is applying exactly the same amount of weight force down on Georgina's hand as her hand is applying a reaction force back on the ball, which is making it stationary. So we have that notion of 0 net force there. This time, Georgina, what we're going to try and do is we're going to try and show Newton's second law.
What's that?
Right, I'm going to throw the ball up to you, and you're going to do a header.
Okay.
You want to do it?
Yeah.
Right, so the first one, I'm going to throw it up to you, and I want you to do it really gently.
Okay.
Real gentle header. You need to be in the camera. Come forward a little bit. Ready? Really gentle, like just a oof. Ready? Go. All right, so we'll do it one more time, same. Okay, so in that example there, you can see that Georgina's applying a force from there forward, and it's kind of so-so force, not too strong. It's kind of gentle, so the acceleration of the ball is kind of gradual, and it comes down to me in a nice gentle way. If she gives it one of those, I don't know if you're still in the camera shot at the moment, Georgina, but yeah, I think you are. You're okay there. But this time, I want you to head it quite hard. I want you to head it to here. Okay, you ready? So at me. Don't break the computer behind me. Ready? Go. Okay, one more. Ooh. Okay, good. So in that example, we've got that idea of a greater force creating a greater acceleration. That Newton's second law. Georgina, come here a sec. How does your head feel?
Fine.
But did
It
you
hurts a bit.
say again?
It hurts a bit.
It hurts a bit. Why? Where?
Because like here, where you like hit it.
Okay, and that's the point I want to make. So Georgina's applying some newtons to that ball there, and the ball is applying the same amount of newtons exactly back in the same opposite direction back on Georgina in that way. Okay, and so yeah, just an impromptu example. How are we doing? Are we ready?
Well, hopefully we'll be all right.
Okay, we'll give this another go. If for some reason this doesn't work, we'll have to figure out another way and produce this for people sort of on demand afterwards, I think. Right, let's have a little try, shall we?
Yeah,
let's go.
Let's go.
So I clearly took far too long on that first part of this session. So let's do this bit pretty quickly. I'm going to focus specifically here on the graphical representation of these concepts of distance and velocity. Okay, so my focus here is to focus on that. We're obviously going to touch on notions of the units and the equations for these principles, but I'm ultimately going to focus on the graphs. So let's have a look here. So we're first of all going to look at distance time graphs. Okay, so distance time, that's what we've got first of all, distance time graphs. And look out for these in your exam questions, because I have found, again, they're simple concepts, but sometimes trip students up for some reason. So let's have a look at these in a bit of detail. So look, let's take example number 1 here. We have got the idea of a stationary object. Now that does not mean your pencil, pens and your rulers that you have in a lovely pencil case. It means an object that is not moving. All right, and we see here that effectively, if we've got distance on the y-axis and time on the x-axis, what we should see from a stationary object is that the distance travelled does not change as time passes. So look, time is passing like this, okay, time is passing there, and the distance, whether it goes up or goes down, the distance travelled is remaining what? Constant. So in other words here, we've got a stationary object. So what would be an example of this? Somebody waiting at a sprint start, a balance, a rugby scrum, all of these would be, assuming it's not moving of course, all of these would be examples of how we'd see this distance time graph actually playing out. Okay, so the start, before the gun goes in 100 or 200 meters, we'd expect to see this kind of shape because there's no distance being changed or traveled as time passes. The only sort of aspect of that you might want to be careful of course, we don't tend to measure time before the race actually starts, but nevertheless. Here what we've got is a different principle for number 2. Here we've got the idea of constant velocity. So think this idea through. As time progresses, we should have distance going up proportionally. Okay, we should have distance increasing proportionally. Okay, so what do we find here? We find that here we have time passing and distance increasing proportionately to that time. So as a result of that, we could define this as something like middle of a sprint. We could describe this as some kind of top speed. And here's an interesting one for you. Think about this one. A shot put in flight. Now remember, we're not drawing the direction of the shot. We're drawing the fact that the shot is traveling a certain set distance within a period of time. Okay, so this would be really a good example of a shot put in flight. Now, if we carry, let's imagine that this here is the landing point of the shot. What would happen to the distance at that point? What would the curve actually look like? And you might be able to say that at that point then, the curve effectively carries on like that, because of course the distance until the shot is actually lifted off the ground doesn't move. That's assuming it sort of stops dead, it doesn't roll on. But we'd expect the distance to stay at that point. This point, what's I think world record holders for women's about 19 meters 50. So let's say that this is 19 meters 51 here. Okay, the shot would travel through the air, would land at this point here, and then would remain at 19 meters 51. In other words, we'd get a constant velocity followed by stationary object. So you can get kind of compound graphs, and it's interesting to think about it in that way. This is what we would describe as number 3 here. This is what we describe as an accelerating body. So the distance covered is increasing per unit of time. Let me write that in for you. Distance travelled is increasing per unit of time, or per second you could say, of course. So if we look at this second here, for example, between here and here, okay, the distance travelled only goes from here to about here. Okay, if we look at this part here, if we were to track this up, okay, we can see here that all of this distance is increased within that period of time. Okay, within that period of time, we've got this amount of distance compared to this little amount of distance here being actually travelled per that unit of time. In other words, the body is accelerating. We can see that by the shape of the curve. And fourthly, and finally, we have a decelerating body here. So again, what we've got here is the distance travel is, we just literally changed that word, decreasing per unit of time. And of course, what we've got at the top of this curve here, we've effectively got our stationary body here, haven't we? Okay, we're now on to stationary over here. Okay, here we've got the body is decelerating until it effectively stops moving there, and it ultimately slows down to a static point. And again, we've got the distance traveled is decreasing per unit of time. Now, here's some compound graphs. We might expect a graph like this for something like an amateur sprinter. You know, if I was to sprint 100 meters, certainly 200 meters, but even 100 meters, what would we find? We'd expect to find part A, which of course is a shape of acceleration. Remind yourself above, we have this shape is happening here, acceleration. We then have this red section in the middle. This is, we know that this is the time and the distance traveled are proportionate. So this is what we call constant velocity, or we might want to call it terminal velocity, top speed. My top speed is not particularly high, unfortunately. And then here we have the distance traveled is decreasing per unit of time. So of course here we've got deceleration. In other words, we've got three distinct stages within our performance here. Let's call this 100 meters for our argument's sake. Okay, we've got three distinct stages, and we can illustrate what's happening with a distance time graph. Now, this is exactly the same, apart from this is what we might call an elite performer. And what is the difference here? Well, the difference is that they accelerate, perhaps they accelerate more rapidly, and of course they hit terminal velocity, constant velocity, and that continues until the end of the race. Remember, this point here is the end of the race. Okay, and if we track it down, you know, we're getting down to something like 10 seconds, that elite level, something between, well, I mean, world record levels is what is Bolt's men's record, something like 9.57 or something like that at the moment. And of course, then the women's world record comes in around about 10.5, I think it is. And then, of course, a lot of 100 meters for both men and women get run between 10 seconds and about 11.2 seconds. Okay, so this kind of elite level here, you're not going to get, at 100 meters at least, you're not going to get that kind of deceleration curve off at the end, because they don't slow down as they finish, generally speaking. Now remember, that is for 100 meters. Now if we come down, of course, we're going to look at here in a second in this question, you'll notice that we've got that shape, but this is an elite sprinter. Josh is elite sprinting, but he decelerates at the end. Okay, and that's because he's a 200 meter runner. Okay, or he's running at 200 meters there, but more of that in a second. So let's now have a look at velocity time graphs. And again, this might be the bit you find confusing, because you're thinking, right, I've got those distance time graphs. They seem really sensible. I get that. How then do I link? How can I differentiate these to with the velocity time graphs? Well, the key thing is being able to accurately interpret the graph. If it confuses you that this one and this one look the same, the reason that is happening is because we don't have a clear enough concept of distance and velocity, and that's the bit to ultimately work on. So let's have a look at this first one as an example. So number one, we've got here constant velocity. So we're saying that as time progresses, velocity is consistent. In other words, it's constant, so therefore it's constant velocity. Now in this case, we've got constant velocity here, it's at whatever x meters per second. Okay, so this could be something like middle of a race, as we've looked at before, middle of a race. We could look at something here again, something in flight, so heavy object in flight, heavy object in flight. Okay, so something like our shot example, or a long jumper traveling through the air would be a good example as well. So we've got this constant velocity there. Okay, it doesn't change, but that does change if we look at example 2. And now we're looking at an accelerating body. And again, this time the rate of change or the rate of change of distance increases over time. So our velocity increases over time. Why? Because the body is accelerating. Okay, so As time passes, the rate of change of velocity is getting greater and greater and greater, and that is an example of acceleration. So we could be looking at examples such as ball leaving racket, or you could say club or paddle. There, we could talk about something like start of a sprint, or we could be looking at something like ball leaving hand. Okay, they would all be characterized by this shape, this acceleration shape. Here we've got the deceleration of a body, so the velocity is decreasing over time. Remember, if this was at constant velocity, it would carry on like that. If it was getting faster, it would go like that. Okay, so this is decelerating until it comes down to 0. Okay, so we could be talking about something like tackle. You know, so someone's running forward with a ball in rugby, for example, and they are effectively at this point here. They are tackled until this point here. Remember this period of time. They come to be completely stationary from that point. That would be a classic example. We could be thinking about something like a catch. You know, the ball enters the hand here, and as the catcher cushions the ball into their hands, it eventually comes to rest as they slow the ball down and catch the ball. So those would be good examples of a decelerating body. You could also talk about, you know, like a sprint after the final, after the finishing line, I suppose, something like that. And this is one that really confuses students a lot of the time. That was number 3 there. This is what we call a change of direction. And it's probably the most difficult application of these particular principles. And it leads us to talk about what we'd call negative and positive velocity. Okay, so it's important to get this principle in mind. So think about this as something like a tennis player moving to their right to strike the ball and then shifting to their left. Or it could be someone who's jumping up in the air, and as they come back down to, as they reach their peak, they come back down and then land on the ground and kind of lower themselves down a little bit to readjust themselves. So here what we've got is, in this first part here, this part A, we've got what we'd call positive velocity. And if you notice here, we've effectively got acceleration, we've got a touch of constant velocity at the top, and then we've got deceleration down this side. Okay, but of course what would then happen as we push off in the other direction, we're still accelerating, but we've now got negative acceleration because we're now going in the opposite direction. Something like, you know, instead of moving to the right, which was this bit, we're now moving to the left, which is this bit. And then we get kind of like this little bit of constant velocity, and then eventually we decelerate again to get back here. And this could be, for example, our ready position. Okay, so we've got our positive and our negative velocity. Now, the only difference between this blue area and this red area, well, the blue area is bigger, so we reach a higher peak velocity, for example, and the red sort of salmon area is exactly the same. We reach a lower peak velocity, but in this case we're going in a different direction, and we can illustrate that in this way. Let's have a look at the question. Now, first of all, I need to correct a mistake. There's this word here, I think yours is actually correct, but mine's wrong. This says velocity time graph. We're actually looking here at a distance time graph. So Josh, our sprinter, recently raced in a 200-meter event and produced the following distance time graph. Accurately describe Josh's performance at the start, middle and end of the race. Well, if we're going to describe things, we're going to say is characterized by. We're going to say is composed of. We're going to say is like. We might even just say is. We're saying what the thing is, what its characteristics are. The characteristics of the shape are, it is characterized by. Let's have a look at how we go about answering this. We already know this shape is basically this one, right? So we already know we've basically got this principle here. So let's see if we can actually put it into writing. So we've got here, we're going to break it into 3 parts, which are going to be the start, the middle, and the end. So let's have a look at how we get on. The start, so no introduction here, I'm just going straight into answering. The start is characterized by, so I'm describing, is characterized by acceleration. So first of all, I'm going to say that the start is acceleration because the rate of change of distance is increasing. So I'm saying the rate of change of distance is increasing Therefore, we've got acceleration. And again, I'm probably going to end up with a submax there. I'm probably going to get 2 marks maximum for the start, 2 marks maximum for the middle, 2 marks maximum for the end of the race. But it's nice and simple there. I'm not going on about this. I'm saying it's acceleration. Why? Because the rate of change of distance is increasing. Okay, simple, done, move on. So now we're going to look for our next 2 marks. The middle is characterized by, so I'm describing again, constant velocity, or we could call it terminal velocity. I know this because the rate of change of distance is proportionate with the time passing. Exactly what we looked at above. Nice. Thirdly, the end is characterized by deceleration. Okay, great. How do we know that? How do we know that this part is deceleration? I know this because the rate of change of distance is decreasing as time passes. So I've shown my understanding of distance time graphs. I've been able to apply it to this specific curve. You know, if this curve had looked like this, for example, the end of the race, let's say this point here to this point here, would again have been constant velocity. But we don't have that, do we? We have a decelerating body, and we have to express it in that way. Now, as I said before, this is a 200-meter race here, so we might expect the runner to slow down a little. Depends how they've tactically run their race, I suppose, but in this case they seem to have run like a sort of what you might call an average race structure, where they've gone out, they've accelerated hard at the start and they've tried to maintain their speed at the end but haven't quite been able to manage it. But there I'm describing the different features of that graphical format of distance and time.
Okay. Oh, we got a really funny kind of orangey red glow in this shot. I kind of see it in the camera.
Yeah, a little bit. I think because the light is a bit
different,
lower.
no? Well, never mind.
It's sort of intimate. Let's call it intimate.
Okay. Let's leave that point.
Right. Yeah, I've got a couple of questions, James.
Mm-hmm.
Could you explain to me, please, how do you calculate velocity? Okay,
so for velocity, the key thing with that is that we need to know that that's distance over time. Okay, so if anything moves this distance, however long that takes, you know, if we divide the distance by the time, we're going to get the average velocity of that. What I'd say to the students out there, though, is that you might want to think about that in terms of not just a whole sort of average velocity of, say, 100 meters or 200 meters, as we looked at there, but we want to look at something, you might want to look at sort of segment times to see the different average velocities per 10 meters, for example. That would be a really good example of how we do that. And we need to remember as well that the unit for velocity is meters per second. Okay, meters per second. So if you think about that, the units there, where do the meters and the per seconds come from? Well, it's distance divided by time. Well, the meters come from the distance and the seconds come from the time. So meters per second, distance per time. So that's where that unit actually comes from. Okay, so it's not, you know, if you can't remember a unit, what I would suggest, let's say you're given the equation in the question. Let's say you can't remember the unit. Take the units for the different elements that are in the equation. In this case, distance, meters, time, seconds, meters per second. And it'll give you, you'll be pretty close with that. We don't always call it the same thing. Often things are named after scientists. Newtons is a good example. Newton meters, the good examples. But generally speaking, it works well. And actually, a good examiner, even if you excuse me, even if you don't put like the official term for the unit, if you construct it correctly, should give you the mark. So yeah.
And what about acceleration?
Okay, that's more complicated, but it's perfectly achievable as well. So acceleration, you actually have to calculate the velocity first. So we calculate acceleration by final velocity minus initial velocity over time taken. Okay, so if you think about that, let's say we're taking a 10-meter segment of a 200-meter race, and the end velocity of that segment is what we'd call the terminal velocity, is, let's say, it's 10 meters per second, and the initial velocity where they started that 10 meters was 8 meters per second. Okay, the difference, the final velocity minus the initial velocity, is 2 meters per second divided by time. Let's say it took 1 second. So 2 divided by 1, the acceleration would be 2 meters per second squared. Okay, so 2 meters per second per second. Okay, and that's how we do it. So it's final velocity minus initial velocity over time taken. Now, I think I'm right in recalling, I do check this with your exam board because I don't want to be held to account on this one, but I believe the only exam board that require you to know the unit of acceleration is OCR. I might check that and put that in a comment in the YouTube chat, but just check on your specification whether that's required. I know it's required on OCR, but I just can't remember with AQ and EdXL off the top of my head. So it would be worth just checking that one. But it should be intuitive to you. Change of velocity over time. So final velocity minus initial velocity over time. Change in velocity over time. And you can calculate these things. We've got some really nice resources in the Teaching Biomechanics pack which get you to actually calculate these things through experimental work. So I'd encourage you guys to have a look at that as well. Any other questions, Marta?
No more questions.
Okay, super. So we'll leave it there. We hope on Wednesday to be in our official office, actually in Classroom 21 when we broadcast on Wednesday. That is the plan. You guys have obviously got your exams approaching. I believe the first one is on the 11th of June if you're a Year 13 student. I think I've got the dates right. So obviously it's coming up for you guys. Get yourselves involved with these shows that we're doing. If you're not using the EverLearner.com already to help you with your revision, bluntly, you're a fool. There are free trials available to everyone. You don't need to pay a penny. Just sign up for a free trial and cancel it after your exam if that's what you want to do. And it's going to help you. Okay, so go and have a look at it. There's unbelievable amounts of quizzing and testing within that site. You get my teaching, all of my teaching available to you when you need it, so you can dip in and dip out, take the bits that you want to take at particular moments. It's all self-paced. All of the little clips are about 10 minutes long approximately. Go and get involved with that. It really, really, really would be daft to do these exams without having looked into that, without using that resource. So if you're not using it already, you should go and have a look. And that goes for teachers as well, especially if you're using my PE exam, then you've already got access to the EverLearn. You should give your students access to that. It's going to help them. So yeah, so that's that. Okay, good. We're happy. All right, I'm happy. I wish you a very good Monday. I'm about to go to the executive meeting for my football club, which thank goodness tonight is in the pub, because otherwise it's going to be a very boring, tedious agenda to be in sort of a clubhouse environment. So I'm going to sit quietly and sip something cold later on. I wish you guys a very good evening. Look after yourselves, and we'll see you Wednesday from our proper broadcast studio. We're with it. Oh, and big thank you to Georgina for doing the little demonstrations for us earlier and getting us out as a bit of a sticky patch. All right, thanks guys. Have a good evening, and I wish you the very best.
The traditional classroom environment does one. Students that don't fit this pace of learning begin to lose confidence. The problem is the current learning model has holes in it. Luckily, the EverLearner.com is here to fill those holes. With the EverLearner Classroom, each student is given a chance to master each subject at their own pace. With thousands of video tutorials and tens of thousands of automated questions on the site, students can progress at their own individual pace. And because every interaction is tracked within the site, teachers can review students' progress and gain access to razor-sharp data. Teachers will have more time to engage with small groups and be better informed of where their time and support is needed. With the EverLearner, teachers can leave the traditional model behind and become facilitators, coaches, and inspirers. There's a reason we have over 100,000 registered students. To learn more, visit our website today.